just for a second, that you're strapping yourself into the driver's seat of a car.
Okay.
But, there's no seatbelt. There are 0 airbags.
Sounds dangerous.
Right. And your literal biological job for the day is to accelerate to highway speeds and then simply slam your face directly into a solid, unforgiving oak tree.
Just right into it.
Straight into it, over and over again. And the craziest part of this whole scenario, you have to survive this completely unharmed thousands of times a day just to get your breakfast.
It's a phenomenal physical extreme when you think about it. You're looking at a creature subjected to forces that would just instantly concuss, or, well, frankly, kill almost any other vertebrate on the planet.
Yeah, there's no middle ground there.
Exactly. There's no middle ground in that kind of impact. You either have the structural engineering to withstand it, or you shatter.
Which sounds like some kind of, physics-defying cartoon, but that's the baseline existence for the subject of our deep dive today.
It really is.
We're looking at an absolute marvel of biological engineering, the woodpecker.
Yep.
But we aren't just looking at the generic birds you might see at a typical backyard feeder here. We're zeroing in on a highly specialized, incredibly elusive, and honestly, strangely contradictory bird from South Africa called the Knysna woodpecker. And for anyone taking notes, that's spelled Knysna.
Right. The scientific designation is Campanther notata.
Mm-hmm.
And when you lay out the stack of ornithological research, the field observation data, and the taxonomic profiles we've gathered for this deep dive, this really fascinating narrative emerges.
Absolutely.
Because this is not just your standard rundown of a bird hitting a tree. We are looking at a literal masterclass in extreme anatomical adaptation, brilliant architectural strategy, and frankly, some glaring scientific mysteries that have just tripped up researchers for decades.
Yeah, that database typo we found is wild, but we'll get to that. So our mission today, specifically tailored for you listening, is to synthesize all these sources and pull out the absolute best, most surprising insights.
Right.
We're going to unpack the highly unusual habits that keep this specific bird alive in dense canopies. We'll analyze their borderline paranoid nesting strategies, and we'll decode the secrets to actually finding them in the wild. Because, they absolutely do not make it easy.
No, they are notoriously difficult to track. So, to set the stage geographically for you, we need to picture the coastal forests of South Africa.
Okay.
We're talking about the Western Cape, the Eastern Cape, and pushing marginally into the southern edges of KwaZulu-Natal.
Right.
And taxonomically, they belong to a genus you mentioned, Campethera. That name actually derives from the ancient Greek words kampi, which means caterpillar.
Oh, cool.
And theris, meaning hunter.
Caterpillar hunter. I love that. I really love when scientific names actually give you a vivid job description rather than just, a Latinized version of whoever discovered the bird.
It's remarkably descriptive, yeah. The Campethera genus represents a group of sub-Saharan woodpeckers that are generally characterized by this olive-green plumage. But more importantly, they have an absolute dietary obsession with hunting insects.
Ants and termites mostly, right?
Specifically, yes. They aren't the classic deep forest lumberjacks you might picture, hammering into primary rainforest timber. They tend to prefer open woodlands, savannas, and these coastal thickets.
I actually want to stop right there and look closer at that mental image, because when most of us think of a woodpecker, we all have the exact same picture in our heads.
Right, the classic pose.
Yeah, you see a bird plastered vertically onto the side of a massive straight pine tree trunk, using its tail as like a kickstand, just going to town on the bark.
Exactly.
But looking at the anatomical data for this African genus, and the Knysna in particular, it looks like they are doing something completely different. I almost thought I was reading about a different type of bird entirely.
That perceived contradiction is really the key to understanding the Knysna woodpecker. Their specific anatomy forces a complete behavioral shift. But, to truly appreciate how they break the woodpecker mold, we first have to understand the baseline engineering that allows them to survive the violent impacts you described earlier.
Right, the face slamming mechanism.
Right.
Because the physics of this are just staggering. If a human experiences, 100 Gs of force in a car crash, that is a catastrophic, usually fatal event.
Oh, easily.
But a typical woodpecker experiences over 1,000 Gs every single time its beak strikes wood.
The forces are just staggering. So to survive that repeated trauma without suffering chronic traumatic encephalopathy, essentially, without turning their brains to mush,
right,
the Knysna woodpecker possesses a skull constructed from a specialized type of dense, spongy bone.
Spongy bone?
Yeah, it's highly trabecular, meaning it's structured like a microscopic lattice or a honeycomb. So when the beak strikes wood, that spongy lattice absorbs and disperses the high-frequency vibrations before they can reach the brain case.
I was reading about this, and it made me think of modern sports safety equipment. But it's not just a hard outer shell, right? It's like wearing a helmet that is entirely filled with microscopic crumple zones that instantly reset after every single hit.
That is an excellent comparison, actually. Furthermore, the surrounding neck muscles act as massive, natural shock absorbers.
Wow.
They tense up milliseconds before impact to stabilize the cervical spine. But the brain itself has the most fascinating defense mechanism.
Okay.
In humans, our brains float in a relatively large pool of cerebrospinal fluid. So in a sudden deceleration, our brain sloshes forward and strikes the inside of the skull. That's what causes a concussion.
Oh, so our built-in cushioning is actually our downfall in a high-speed collision. Like the fluid gives the brain room to build up momentum before hitting the skull wall.
Precisely. The woodpecker solves this by virtually eliminating that fluid space.
Just getting rid of it.
Yeah, the bird's brain is tightly packed within the cranium. Because there's no room for the brain to slosh around, there's no secondary internal impact. The tight packing prevents those microconcussions entirely.
It's basically a Formula One driver's safety setup. You know, they wear that specialized HANS device, the head and neck support system, to stop their head from snapping forward in a crash.
Right.
The Knysna woodpecker basically has a HANS device, a football helmet, and a custom shock absorption system all built directly into its skeleton.
It does. And the structural modifications extend all the way down to the beak. The bill is chisel-like, sure, but the lower mandible is actually slightly longer than the upper mandible.
Oh, really? An overbite, or I guess an underbite.
An underbite, essentially. Yeah. And this asymmetry is crucial. It directs the mechanical stress of the impact away from the brain case and down into the reinforced base of the skull and those neck muscles.
That's so smart.
But structural integrity is only half the battle. Think about the environmental byproduct of chiseling dry wood.
Oh, sawdust. Just clouds of microshrapnel flying directly into your face with every single strike.
Exactly, which would normally blind an animal or just destroy its respiratory system.
Right.
So to combat this, they have specialized bristle-like feathers growing right over their nostrils to act as a physical air filter, blocking the wood dust from being inhaled.
Wow.
And to protect their eyes, they have highly developed nictitating membrane.
That's the third eyelid, right?
Yes, it's a translucent membrane that sweeps across the eye. But it doesn't just blink randomly, you know. It deploys like built-in safety goggles, clamping down tightly across the eye mere milliseconds before the beak makes contact with the wood.
Milliseconds?
Yeah, it shields the cornea from flying debris while still allowing the bird to see the impact zone because it's translucent.
Built-in safety goggles that trigger automatically. That is just incredible. Okay, so that establishes their heavy-duty toolkit. They are completely built for impact.
Very much so.
But you mentioned earlier that the Knysna breaks the mold of the classic vertical trunk hugger. And looking at the field data, the primary reason for this seems to be a really strange evolutionary compromise regarding their tail.
Yes, and this is where their unique ecology really begins to shine. Like all true woodpeckers, the Knysna has what we call zygodactyl feet.
Zygodactyl. So instead of 3 toes forward and 1 back like a normal songbird, they have 2 toes pointing forward and 2 pointing backward.
Correct. And combined with sharp, deeply curved claws, this arrangement provides an iron grip. It operates like a biological clamp.
Right.
It allows them to latch onto a vertical surface and completely defy gravity. But the crucial divergence from the typical woodpecker blueprint lies in those tail feathers.
Okay, how so?
Well, a highly specialized vertical woodpecker, think of the large pileated woodpeckers in North America, has fully stiffened tail feathers, known as rectrices. They jam this rigid tail against the tree trunk, literally acting as the third leg of a tripod.
Yeah, I've seen that. They lean back on the tail, which anchors their lower body, and that allows them to swing their upper body and head like a sledgehammer with maximal leverage.
Exactly. But the Knysna woodpecker has only partially stiffened rectrices. The feathers are flexible.
Which honestly puzzled me when I was reviewing the anatomical charts for this. Because, evolutionarily speaking, why give a woodpecker a halfway stiff tail?
It seems counterintuitive.
Right. If your entire survival depends on hammering wood, trading away your tripod anchor seems like a massive downgrade. It's like giving a kangaroo a weak jump. Why would they trade that leverage away?
Well, if we expand our view to the specific environment they inhabit, that apparent downgrade transforms into a masterstroke of adaptation.
Yeah.
Because the Knysna woodpecker does not spend its life clinging to massive, vertical, open tree trunks.
Oh, I see.
That flexible tail allows them to forage horizontally.
Horizontal foraging. So they're moving along the branches themselves, not just the main pillar of the tree.
Exactly. They navigate the undersides of horizontal limbs. They scramble through thin, delicate, tangled branches within the dense foliage of the forest canopy.
Ah, okay.
A fully stiff, rigid tail, that heavy-duty tripod would act like a rigid plank strapped to their back in that environment. It would constantly snag on leaves, vines, and secondary branches, completely ruining their agility.
Oh, that makes perfect sense now. They trade the absolute brute force leverage of the vertical stance for, like, gymnastic agility in the canopy.
Precisely.
It totally expands their hunting grounds. They aren't restricted to the trunk. They have access to the entire three-dimensional architecture of the tree.
And that horizontal agility is absolutely essential for their specific diet. We mentioned the caterpillar hunter translation earlier, but scientifically, the Knysna is highly specialized in myrmecophagy.
Myrmecophagy. That is a phenomenal word for an animal that eats ants and termites.
It's a great word. Their entire caloric intake relies heavily on arboreal ants, termites specifically targeting the nutrient-dense eggs and pupa spiders, and wood-boring beetle larvae.
Quite the menu.
Indeed. To find this prey, they forage systematically across all levels of the tree canopy. They use that agility to creep along horizontal branches, using their chisel beak to peel back loose layers of bark or probe into narrow, naturally occurring cracks. But they also hunt acoustically.
Wait, acoustically?
Yeah, they tap lightly along the branch to locate hollow chambers hidden deep inside the dead wood.
This is fascinating. They're basically performing a sonic ultrasound on the branch. They tap, the wood density changes, they hear a hollow echo, and they know there's a gallery of termites hiding inside.
Right.
So they chisel a small breach hole, but the hole they make is often tiny, and those insect galleries can run deep into the heartwood. How do they physically extract the bugs?
Well, this brings us to what might be the most bizarre and highly engineered piece of soft tissue in the avian world: the woodpecker tongue.
Oh, boy.
Once they breach a chamber, they deploy a tongue that is astonishingly long. It's coated in highly viscous, sticky saliva, and the tip is rigid and lined with rear-facing barbs.
That's a sticky harpoon.
A very literal harpoon. They thread this incredibly long tongue deep into the winding tunnels of the insect gallery, spear the larvae or snag the worker termites on the sticky barbs, and just pull them out.
Wow.
But the mechanical problem of a tongue that long is storage. It's much longer than the beak, and even longer than the skull itself. It cannot simply rest in the mouth cavity.
Yeah, I was looking at the diagram of this in the source material, and it honestly looks like an alien parasite living inside the bird's head. The tongue is supported by this massive, elongated bone structure.
The hyoid apparatus.
Right, the hyoid.
In humans, the hyoid is a small, horseshoe-shaped bone in the neck that anchors the tongue root. But in the Knysna woodpecker, the horns of the hyoid bone are monstrously elongated.
How long are we talking?
Well, they split at the base of the throat, wind all the way up the back of the neck, curve over the top of the skull beneath the skin, and anchor deep in the nasal cavity. Sometimes they even wrap around the right eye socket.
That is wild. The structural support for their tongue wraps entirely around the outside of their skull. That's just staggering.
It functions like a biological spring mechanism. When specialized muscles contract, the hyoid apparatus slides forward, launching the tongue out of the beak with incredible speed and precision.
Right.
And as an unintended evolutionary bonus, when the tongue is retracted and those cartilaginous hyoid horns are pulled tight over the skull, they act as an additional layer of shock absorption.
Oh, wow.
It's almost like a bungee cord strapping the brain case tightly together during impact.
It is wildly efficient. Bizarre, but efficient. But, looking at this extreme dietary specialization, the acoustic hunting, the harpoon tongue, the canopy agility, it begs a massive ecological question.
What's that?
If your entire existence revolves around pulling ants out of wood, what happens when there's a drought or a cold snap and the insect populations crash? Does a bird this hyper-specialized just starve?
You would think so, given how niche their physical tools are. But the observational data reveals a surprising behavioral elasticity. Yeah. During seasonal periods of food scarcity, when the arboreal ant and termite populations dip, the Knysna woodpecker will completely switch its foraging strategy. They actually supplement their diet with wild fruits, berries, and figs.
No way. So the hardcore brain-cushioned ant harpooner is actually an opportunistic omnivore when times get tough.
Their adaptability is their greatest asset. Field researchers have even documented them moving out of the forest entirely during harsh seasons. visiting mature suburban gardens to feed on high-energy suet blocks from artificial bird feeders.
I find that incredibly endearing, honestly. This marvel of wild engineering just hanging upside down on a plastic feeder in someone's backyard.
It's quite a sight.
And that specific behavior, hanging upside down, transitions us perfectly into the next major phase of their life cycle. Because of that same anatomical quirk we discussed, the flexible tail that allows them to scramble horizontally, well, it dictates the deeply paranoid, ingenious way they build their homes.
Yes. The architecture of the Knysna woodpecker nest is a direct consequence of their physical adaptations and the intense predation pressures of their environment.
I really want to spend some serious time on this because life in the cavity is fascinating. Let's look at the basic parameters first.
Okay.
According to the data, their breeding season runs roughly from August to February, with a massive peak in nesting activity occurring in October.
Correct.
They are strictly monogamous during the season, and they are solitary nesters. You aren't going to find a noisy apartment complex of woodpeckers sharing a single dead tree.
Definitely not.
But the sheer labor involved in creating the nest is intense, and both the male and the female share the excavation duties.
Well, it takes weeks of dedicated, exhausting labor to carve out a secure cavity. But the critical detail is the location they choose.
Right.
They don't just pick a broad, flat section of a massive trunk. They specifically bore their nesting cavity into the underside of a dead or decaying horizontal branch.
The underside.
Yes. Alternatively, if they use a main trunk, it must be leaning at a severe angle, and they will excavate on the downward-facing slope.
See, when I first read that, I couldn't understand it. Clinging upside down to sleep is one thing. But clinging upside down, using neck muscles to swing your head and chisel solid wood for weeks, seems like an agonizing waste of energy.
It is extremely demanding.
Right. Why make it so physically demanding on yourself?
It requires immense energy, yes, but the evolutionary payoff is security. There are two very practical, life-saving reasons for this underside architecture.
Okay, let's hear them.
First, consider the climate. The coastal forests of South Africa experience heavy rainfall. If you excavate a hole in the top or the side of a branch, it acts as a funnel.
Oh, sure.
The cavity will flood, chilling the eggs or just drowning the chicks. By placing the entrance on the underside, gravity ensures the nest remains completely dry, even in a torrential downpour.
So gravity acts as a natural roof. That's clever. But the second reason has to do with who else is living in that tree, right?
Predation. The Afro-temperate forests and coastal thickets are home to numerous climbing predators. We're talking arboreal snakes like the boomslang, monitor lizards, and small predatory mammals like genets.
Right.
These predators are adept at climbing vertical trunks. But to access a hole on the underside of a smooth, dead branch, a predator has to somehow defy gravity, clinging upside down without the benefit of the woodpecker's zygodactyl grip.
Yeah, snakes don't have toes.
Exactly. And simultaneously, they're trying to reach their head upward into a tight hole. It's incredibly difficult.
It's basically an architectural moat. They use the geometry of the tree to completely neutralize the climbing advantages of snakes and mammals.
It is.
That is brilliant. And the dimensions they are carving out are incredibly precise to maximize that security, too. The entrance hole is only about 45 millimeters in diameter.
Just under 2 inches. It is an incredibly tight squeeze. It's barely wider than the circumference of the adult bird itself. This further restricts the size of any predator that actually manages to navigate the underside of the branch.
Right, they just can't fit. And then once you pass that tiny downward-facing entrance, the chamber drops down vertically into the core of the branch, usually 150 to 300 millimeters deep.
Right.
So you have a secure, dry, predator-proof bunker dropping 6 to 12 inches into the deadwood. And interestingly, they don't bring in any soft materials, right? No moss, no feathers, no grass to line the nest.
True woodpeckers rarely do. They rely on the byproduct of their construction. They leave a thick layer of loose wood chips and sawdust at the bottom of the deep chamber.
Built-in bedding.
Exactly.
Huh?
This wood chip layer acts as insulation and a soft cushion for the female to lay a clutch of 2 to 4 glossy white eggs. And because excavating this fortress is so energy-intensive, the pair exhibits incredibly strong site fidelity.
Meaning they come back to the same spot.
Yes. If a territory remains productive and the dead tree doesn't fall, a pair will reuse the same tree, sometimes even re-excavating the exact same cavity for many consecutive years.
Okay, so the parents share the excavation, they build an upside-down fortress, the female lays the eggs, and both parents share the incubation duties for roughly 13 to 21 days. and then the chicks hatch.
Yes.
And this brings us to a part of the research that honestly had me pausing and questioning the material. There is a massive, glaring contradiction in the taxonomic data regarding what happens next. It's a genuine scientific mystery hidden in the spreadsheets.
Ah, you're referring to the fledgling timeline discrepancy.
Yes, let's break this down because I found it jarring. In some of the standard, highly respected global ornithology databases included in our sources, the kind of databases that serve as the foundation for broader ecological studies.
I read the big ones.
Right. It clearly states that the fledgling period for the Knysna woodpecker is 4 to 6 days, meaning a chick hatches, and less than a week later, it flies out of the nest.
Which is an astonishingly rapid developmental timeline.
It's practically teleportation from egg to adult. But then I looked at the specific localized field studies in our stack, observations by researchers sitting in the mud actually watching these specific nests.
And what did they find?
Those field studies state unequivocally that the nestling phase, the time from hatching to leaving the nest, is 21 to 27 days.
A difference of 3 entire weeks.
It's a colossal difference.
Yeah.
Now, my initial thought was to defend the global database. I mean, these massive taxonomic data sets are peer-reviewed. They don't just make typos, right?
You'd hope not.
So I thought, is it biologically possible that the Knysna woodpecker has some kind of hypermetabolism? Could the pressure of predators be so high that evolution forced them to accelerate their growth to a freakish degree, allowing them to fledge in 4 days?
It's a tempting theory, especially when you're dealing with a bird that has so many other extreme adaptations. But to solve this mystery, we must apply the foundational principles of avian biology.
Okay.
We have to look at the condition of the chicks when they hatch. Knysna woodpecker chicks, like all woodpeckers, are altricial.
Contrast that for me, because some birds, like ducks or chickens, are precocial.
Right, exactly. A precocial bird hatches covered in down feathers, its eyes are open, and it can walk or swim and follow its mother within hours. Their development happened largely inside the egg.
Right.
Altricial birds are the exact opposite. A Knysna woodpecker chick hatches completely naked, completely blind, lacking any down, and entirely helpless. They lack basic thermoregulation. They're essentially raw, pink embryos existing outside the shell.
Okay, so we have a blind, naked, freezing pink blob sitting in wood chips.
Now consider the sheer biomechanical complexity of avian flight. To achieve flight, a bird must grow a full coat of down for warmth, then push out specialized pin feathers.
Right.
Those pin feathers must unfurl into mature asymmetrical primary and secondary flight feathers. Simultaneously, the bird must convert the protein it eats into massive pectoral breast muscles required to power the wings.
That's a lot of growing.
And neurologically, the brain must develop the complex motor cortex required for three-dimensional aerial navigation.
Okay, I see where you're going with this.
It is physically, biologically, and metabolically impossible for a naked, blind, altricial vertebrate to synthesize that amount of tissue, bone, feather, and neurological wiring in 96 hours.
It just can't happen.
No amount of hypermetabolism can bypass the basic cell division required. Furthermore, if we perform a comparative analysis with their closest evolutionary cousin, the golden-tailed woodpecker, the established verified nestling period for that bird is 22 to 25 days.
So the 4 to 6 day metric is just completely biologically incompatible with reality.
It is a fiction. What likely happened is a classic transcription error early in the scientific literature.
Like a typo.
Essentially, yes. An early observer perhaps noted a developmental milestone, maybe the day the chick's eyes first open, or the day the dark pin feathers first break through the skin, which often happens around day 5 or 6.
Oh, I see.
That milestone was erroneously recorded under the fledgling column in a dataset. And because global databases often scrape and aggregate older data without field verification, that typo became codified as gospel.
A typo that became scientific dogma. That is a fantastic lesson. It proves why you cannot just blindly trust a database, no matter how authoritative it looks. You always have to step back and ask, does this data actually align with the physical laws of biology?
Critical analysis of the literature is just as important as field observation. The 21 to 27 day timeline is the accurate one.
So for nearly a full month, these blind, naked chicks are trapped in this downward-facing wooden bunker.
Yes.
And for a month, both parents are flying relays, hunting relentlessly, and regurgitating a slurry of partially digested beetles, ants, and spiders into the mouths of their young.
It's exhausting work for the parents.
But as brilliant as that underside entrance is at keeping out snakes and lizards, there is one predator, or rather one parasite, that simply flies right through the front door. The unwelcome guest.
Ah, yes. The scaly-throated honeyguide.
I read the section on brood parasitism, and the mechanics of it are just brutally fascinating. Can we dig into the evolutionary arms race happening here? Because the honey guide doesn't eat the woodpeckers, right? It does something much more insidious.
It does. The scaly-throated honey guide is an obligate brood parasite.
Meaning they have to do this to survive.
Yes. Much like the famous common cuckoo in Europe or the brown-headed cowbird in the Americas, the female honey guide has entirely lost the biological instinct to build a nest, incubate eggs, or feed offspring.
They just outsourced parenting.
Completely. She relies entirely on other species to do the heavy lifting of parenthood, and she specifically targets cavity nesters like the Knysna woodpecker.
But how does she even pull that off? The woodpecker entrance is tiny, and woodpeckers are incredibly aggressive birds with literal chisels attached to their faces. If I'm a woodpecker and a strange bird enters my nest, I'm going to attack it.
Which is why the honey guide relies on stealth, timing, and extreme patience. The female honey guide will silently monitor a woodpecker pair from high in the canopy as they exhaust themselves excavating the nest. She waits for the precise window when the female woodpecker has laid her eggs, but before the parents begin permanent incubation.
When would that be?
There's often a small window of a few hours when the nest is left unguarded while the parents forage.
She waits for them to take a lunch break.
Exactly. In that brief absence, she slips into the downward-facing cavity. In a matter of seconds, she lays a single, thick-shelled white egg directly among the woodpecker's eggs.
Wow.
She may even puncture or remove one of the host's eggs to keep the clutch size consistent, so the woodpeckers don't realize the geometry of the nest has changed. Then she vanishes.
And the woodpecker parents return, see the eggs, and just unknowingly accept the imposter.
They do.
But what happens when they hatch? I know some parasitic chicks, like cuckoos, will literally push the host chicks out of the nest to their death. Does the honey guide do that?
The mechanism of honey guide parasitism is uniquely brutal. Honey guide chicks are often born with highly specialized, sharp hooks on the ends of their beaks.
Oh, no.
Yes. Within hours of hatching, while still completely blind, the honey guide chick uses these temporary mandibular hooks to blindly slash and bite at anything else moving in the cavity.
Yeah, horrifying.
They actively murder the host woodpecker chicks. And even if they don't have the hooks, they hatch earlier, grow faster, and aggressively monopolize all the food the parents bring. The legitimate woodpecker chicks either succumb to the direct attacks or simply starve to death under the parasite.
That is incredibly bleak. The woodpecker parents spend weeks carving a fortress out of solid wood. They spend a month flying relays of regurgitated spiders. They drain massive amounts of physical energy.
Yes.
And the result of their entire reproductive season is that they successfully raise the creature that murdered their children.
It is a continuous, merciless, evolutionary arms race. The woodpeckers constantly evolve to make their nests harder to find and harder to access. And the honey guides constantly evolve better stealth, thicker eggshells, and more lethal chicks to counter those defenses.
Nature does not care about our concepts of fairness. It's just a brutal numbers game. Which is a perfect segue, honestly, because if the honey guide, a bird whose sole evolutionary purpose is to find Knysna woodpecker nests, struggles to locate them, it perfectly explains why human researchers find it nearly impossible.
It really does.
Between hiding the nests on the undersides of dead branches and silently creeping through the dense upper canopy rather than hammering loudly on open trunks, the Knysna woodpecker sounds like a ghost. So how on earth do ornithologists actually track them down?
Locating a Knysna woodpecker requires a deep understanding of their specific habitat restrictions, their acoustic signatures, and a very sharp eye for incredibly subtle visual details.
Okay, let's break that down.
To start, you have to understand their geographic footprint, because if you are looking outside a very specific boundary, you will never find one. They are strict endemics.
Endemic, meaning they evolved in one highly specific region and exist nowhere else on the planet. For the Knysna, that region is solely within the borders of South Africa.
Specifically, they're restricted to a narrow band along the southern and eastern coastal strip, extending slightly into the adjacent interior valleys.
Okay.
We're mapping a territory across the Western Cape, moving east through the Eastern Cape, and just crossing the border into southern KwaZulu-Natal. The total extent of their occurrence is estimated at less than 50,000 square kilometers.
Which sounds like a massive area if you have to walk it. But on a global conservation scale, or even just looking at the African continent, 50,000 square kilometers is a tiny, fragile sliver of land.
It is a highly restricted range, And for decades, the scientific consensus was that they were obligate forest specialists within that range.
Meaning what, exactly?
Meaning researchers believed they required pristine, deep, mature, undisturbed primary forests to survive. If a forest was logged and degraded, it was assumed the woodpeckers vanish entirely.
But the more recent data in our sources suggests that assumption was wrong, right? There is a fascinating study of their habitat adaptability based on atlas data.
Yes. The Southern African Bird Atlas Project 2, commonly referred to as SABAPT.
Right, SABAP2.
This is a massive, ongoing data collection effort that relies heavily on citizen science birders, local conservationists, and field researchers logging precise GPS coordinates of bird sightings over decades.
That's a huge undertaking.
It is. And the SABAP2 data fundamentally changed our understanding of the Knysna woodpecker. It proved they are not delicate forest specialists. They are actually remarkably robust forest generalists.
So they aren't as picky as we thought. If they can't find pristine primary forests, what are they settling for?
Well, you will certainly find them in the classic, mature, Afro-temperate evergreen forests, and in the dense coastal thickets dominated by native white milkwood trees. But the Atlas data shows them thriving in much harsher, scrubbier environments, too.
Like where?
They inhabit dry, thorny valley bushveld. They navigate scrubby thickets dominated by toxic euphorbia plants. They follow wooded ravines deep into otherwise arid landscapes. And they're even found in stands of tall, woody protea bushes.
And the most surprising thing to me was their utilization of completely artificial, human-modified landscapes. The sources specifically mention commercial timber plantations.
Yes, plantations of alien, non-native vegetation. Vast stands of imported eucalyptus and pine trees, which are often considered ecological dead zones for native wildlife, are actually utilized by the Knysna woodpecker, provided there were enough dead snags left standing for nesting and foraging.
That is wild.
Furthermore, as we touched on earlier, they have successfully colonized mature, well-wooded suburban gardens and private estates.
Which is an incredible testament to their adaptability. And the SABAP2 data actually shows that because they can utilize these alien trees in suburban gardens, their range isn't just static, it is actively expanding westward, pushing further into the Western Cape toward towns like Caledon.
Yes.
They are exploiting new human-altered habitats.
They are survivors. But here's the catch for the researcher. Even if you know exactly what habitat to search, and even if you are standing in a suburban garden where a pair is known to live, looking up into the dense canopy of a milkwood or eucalyptus tree, you are almost certainly not going to see them. Their mossy green plumage provides near-perfect camouflage against the foliage, and they don't forage out on the exposed open trunks.
Which means bird watching for this species is actually bird listening.
Yeah.
You have to locate them acoustically before you ever raise your binoculars.
Exactly.
I want to try and translate the acoustic data from the field notes. They have a variety of calls. Both the males and females use a primary contact call to keep track of each other in the dense brush. The phonetics describe it as a high-pitched, almost whining nasal sound, nai-weet, or sometimes written as a drawn-out pia.
It functions as a short-range locational ping. It is distinctive, but not incredibly loud. If they encounter a rival pair or a predator, that single contact note rapidly escalates into a fast, agitated, chattering series of notes.
But if you're trying to find them from a distance, there is one specific call that is the absolute gold standard. The sources refer to it as the SCADE call.
Yes. The SCADE call is their territorial broadcast. It's named for the way the sound is transcribed phonetically, S-K-E-A-D. Though it is a happy coincidence that it shares a name with Cuthbert John Skeed, a highly influential historical South African ornithologist.
Oh, that is a fun coincidence.
The call is a single, incredibly loud, piercing, shrill note. It is designed to cut through the dense acoustic clutter of the forest canopy and can be heard from a significant distance.
Skeed! Just blasting like a siren through the leaves.
Pretty much.
And beyond vocalizing, they also use mechanical sound to communicate. They drum.
Which brings our anatomy discussion full circle. We know they have the specialized spongy bone to absorb high impacts for foraging, but they also weaponize that anatomy for acoustic communication.
How so?
During the breeding season, a male will locate a specific, highly resonant piece of hollow deadwood. He isn't looking for food, he's looking for an acoustic amplifier. He will drum rapidly upon it in short bursts.
It's basically a telegraph system.
Exactly. The drumming serves a dual purpose. It broadcasts a territorial boundary to rival males, warning them away, while simultaneously advertising his fitness and the presence of a high-quality territory to potential mates.
That makes sense.
It's fascinating to note that some other species within the Camphothera genus are actually very poor drummers, or have abandoned drumming entirely in favor of purely vocal communication. But the Knysna retains and utilizes strong drumming behavior.
Okay, so picture the scenario. You're a birder. You've studied the Stab-Up-2 atlas. You drove to a patch of coastal milkwood thicket. You listened carefully, and you heard the loud skeed call and the rapid mechanical drumming.
Okay, you're close.
You follow the sound, you peer through the leaves, and finally, you lock your binoculars onto a green woodpecker clinging to a branch. Success!
Or a total failure.
Wait, what?
Because visual confirmation introduces the most difficult challenge in studying this bird.
Oh, the imposter syndrome. I read this section multiple times because it is incredibly tricky. If you see a green woodpecker in that forest, there is a very high probability you are looking at an entirely different bird. The golden-tailed woodpecker.
Yes, Camphothera abingoni. The golden-tailed woodpecker is a very close evolutionary relative to the Knysna. They share the same genus, the same basic body shape, the same myrmecophagous diet, and similar habitat preferences.
Right.
Crucially, they exhibit what we call sympatry in certain regions.
Sympatry, meaning their geographic ranges physically overlap. They live in the exact same forests in southern KwaZulu-Natal and the inland areas of the Eastern Cape. They are literally neighbors.
So if you are observing a bird in that sympatric zone, you must become an absolute perfectionist with visual identification. The differences are subtle.
What are we looking for?
You have to focus entirely on the ventral markings, the plumage pattern on the breast and belly, and the coloration of the bill. Let's analyze the adult Knysna first.
Okay, the dorsal side, the back and wings, is a dark, muted, mossy olive green. But underneath is what matters. The Knysna, from the chin all the way down to the vent, is heavily marked with distinct, round, black spots, just polka dots everywhere.
Yeah.
And the bill is entirely solidly black.
Correct. Dark green, heavy round spots, black bill. Now contrast that with the adult golden-tailed woodpecker. The golden-tailed is generally a brighter, more yellowish golden green on its back.
Okay.
But underneath, the pattern changes. Instead of round spots, the adult golden-tailed is heavily streaked. It features longitudinal vertical dark lines running down its breast and flanks. Furthermore, its bill is a paler slate gray or horn color, not solid black.
So the mental shortcut is streaks versus spots. If it looks like it has vertical pinstripes on its belly, it's a golden-tailed. If it looks like a green Dalmatian underneath, it's a Knysna.
That's a good way to remember it.
That honestly doesn't sound too complicated for an experienced birder to figure out.
It is perfectly straightforward, right up until the moment you encounter a juvenile bird. This is a phenomenon we can call the juvenile trap.
I was looking at the plumage charts, and this blew my mind. The juvenile golden-tailed does not follow the rules. It doesn't have streaks.
No, it doesn't. Before a golden-tailed woodpecker undergoes its first major molt into adult plumage, its breast and belly are covered entirely in spots.
It makes no sense. Why would a bird that is destined to be streaky grow up spotted? Is it basically wearing its evolutionary past? Like, was their common ancestor spotted and the golden-tailed just grows out of it?
That is actually the prevailing evolutionary theory. The spotted plumage is likely the ancestral trait for this lineage.
Oh, wow.
The Knysna retained the ancestral spots into adulthood, while the golden-tailed evolved the streaked plumage as an adult, perhaps for slightly different camouflage needs in its wider savanna range.
That's fascinating.
However, ontogeny recapitulates phylogeny, meaning the development of the young bird often mirrors the evolutionary history of the species. Thus, the juvenile golden-tailed expresses the ancient spotted trait.
So a juvenile golden-tailed woodpecker looks almost physically identical to an adult Knysna woodpecker.
It is a morphological nightmare for field researchers. A spotted juvenile golden-tailed, especially a female lacking the red malar stripe on the cheek, is nearly indistinguishable from an adult female Knysna at a distance.
That is diabolical. If I'm a researcher conducting a population survey, counting birds in the canopy, aren't I just going to inevitably miscount these populations? I might mark down 10 Knysna woodpeckers, and it turns out 8 of them were just young golden-tailed teenagers.
This precise morphological overlap has severely contaminated the historical data.
Really?
Oh, yes. There are numerous older ornithological records and museum collections claiming the Knysna woodpecker lived much further north along the coast, deep into northern KwaZulu-Natal.
Let me guess. They were wrong.
Completely. Upon modern re-examination of those museum skins, it was discovered that many of those Knysna records were, in fact, misidentified, spotted, juvenile golden-tailed woodpeckers.
The imposter trap completely warped our understanding of their geographic range. It's just another massive lesson in critical observation. First, the 4-day fledgling typo, and now the juvenile camouflage.
You have to be careful.
It really drives home the point that in ornithology, you cannot just look at a bird. You have to understand its deep evolutionary lineage and its exact developmental life stage to know what you are actually seeing.
Exactly. Identification requires context. And speaking of context, I think it's important to briefly touch on the cultural footprint of the bird before we move to its conservation status.
Yeah, let's do that.
Because the scientific Latin and the English common names are only one way to interact with the species. Knowing the local nomenclature provides a richer understanding of how the bird is perceived in its actual environment.
I love diving into local names. In Afrikaans, the language spoken widely across its range, it is known as the Knysna pig, which is a very direct, literal translation, Knysna woodpecker.
Yes, very direct.
In the traditional Xhosa language, primarily spoken in the Eastern Cape, it is referred to as the Eisenkolomthi.
Although researchers must use caution with that term, as Eisenkolomthi is a broader, descriptive name that is sometimes also applied to the much more common cardinal woodpecker. Again, context in the field is everything.
Right, but my absolute favorite descriptor from the literature is the French common name, Pictigre.
The tiger woodpecker.
The tiger woodpecker. It is such a fierce, evocative name for a bird that is basically 7 inches long. But when you look at the heavy, dark spotting on the belly and the muted yellowish-green barring across its back and wings, it does resemble a cryptic tiger pattern.
It does, yes.
It paints a picture of a tiny, heavily camouflaged, insect-harpooning tiger silently prowling through the dense canopy of a milkwood thicket.
It's a beautiful and remarkably accurate descriptor of its ecological niche.
So we have built a comprehensive profile of this tiny tiger. We know it has a highly restricted endemic geographic range. We know it is bound to a highly specific, energy-intensive nesting strategy that requires the undersides of dead branches.
Right.
We know it faces constant pressure from honeyguide brood parasites, and it causes massive identification headaches due to its evolutionary similarity to sympatric species. When you stack all of these restrictive factors together, it naturally forces a massive looming question.
Which is?
How is this bird surviving? Are we on the verge of losing the Knysna woodpecker entirely?
That leads us into the final and perhaps most complex aspect of our deep dive, the survival question. The current conservation status of the Knysna woodpecker is actually the subject of a fascinating debate between global organizations and regional experts.
But I noticed the discrepancy immediately. If you check the global rating provided by the IUCN, the International Union for Conservation of Nature, which is essentially the global authority on species risk, they list the Knysna woodpecker as near threatened, which is a red flag. It implies the species is sliding dangerously close to the vulnerable or endangered categories.
And the IUCN's reasoning is entirely sound when viewed through a macro statistical lens. Their primary metric of concern is the absolute global population size. By any metric, the total number of Knysna woodpeckers is undeniably small.
How small?
The estimates in the literature range somewhat wildly due to the difficulty in surveying them, but the most generous estimates put the total global population at fewer than 10,000 individuals.
10,000 birds total.
And, more concerningly, some refined estimates suggest the number of mature, actively breeding individuals could be as terrifyingly low as 1,500 to 3,300 birds globally.
3,000 mature breeding birds on the entire planet. That is nothing. If a single severe disease ripped through the coastal forest or a massive catastrophic wildfire swept the Eastern Cape, a population that small could functionally collapse in a single season.
Easily.
It sounds incredibly fragile. I completely understand why the IUCN flagged them as near threatened.
The fragility is real. However, there is a strong counterargument presented by the regional South African conservationists and ornithologists who study the bird locally.
Oh.
When the regional red list of birds for South Africa, Lesotho, and Eswatini was updated, they categorized the Knysna woodpecker differently. They listed it as a species of least concern.
Wait, how is that possible? How can the local experts on the ground be significantly less worried than the global experts sitting in an office? Usually it's the exact opposite. The locals are screaming for help while the global agencies move slowly.
It comes down to how different organizations weigh specific data trends. The IUCN heavily penalizes the species for having a tiny absolute population,
Yeah.
but the regional experts base their assessment heavily on the SEBOP2 atlas data we discussed earlier,
Okay.
and the critical metric they extract from that atlas data is population trajectory.
Are the numbers going up or down?
Precisely. When calculating conservation risk, biologists look at population stability over generation lengths, meaning the average age of breeding individuals. The atlas data shows that over the last 3 generations of the Knysna woodpecker, the overall population numbers are remarkably stable.
Oh, that's good news.
There's no evidence of a steep, catastrophic decline. They are not vanishing.
And taking that a step further, the SABAP2 data actually proved they are expanding westward into alien plantations and suburban areas.
Exactly. Because they are not obligate forest specialists, because they possess the behavioral elasticity to forage in dry euphorbia scrub, eat suet from bird feeders, and excavate nests in dead eucalyptus trees, they're holding their ground.
That makes sense.
The regional argument posits that while the total population is undeniably small, it is stable and highly adaptable, and therefore it does not currently meet the strict catastrophic decline criteria required for a threatened status.
It's basically a philosophical debate on what constitutes danger. Is a small but stable population in danger just by virtue of being small? Either way, it is a rare relief to read a conservation study where the local data says actually they are holding their own.
It's refreshing.
But least concern doesn't mean they are invincible. The sources highlight several massive ongoing threats that we cannot ignore if we want them to remain stable.
Stability is not a guarantee of future safety, no. We must acknowledge the historical habitat loss. We discussed the range contraction in KwaZulu-Natal.
Right, the area where they lost ground.
While some of that was data confusion with the golden-tailed juvenile, much of it was a genuine localized extinction. That contraction was driven entirely by human activity, the systemic clearing of native coastal dune forests to plant massive monoculture sugarcane fields and to build expanding coastal townships.
So habitat fragmentation is a permanent looming shadow over their entire range.
It is.
But the threat that really jumped out at me, the one that feels the most immediate, the most solvable, and the most tragically ironic, connects right back to their brilliant architectural nesting strategy. The deadwood problem.
This is the critical bottleneck for their survival. We established early on that they must have dead or decaying wood to excavate their nests.
Right.
The spongy skull and chisel beak are amazing, but they do not typically bore into live, healthy green timber to create a massive nesting chamber. Live wood is too dense, it requires too much energy to excavate, and the flowing sap can flood the chamber or ruin the bird's plumage.
Makes sense.
They require rot. They need the softened heartwood of a dead branch to dig.
Right. They need the structural decay to make the labor manageable, but the problem is human psychology. We actively hate deadwood.
We really do.
If a tree dies in a municipal park or on a farm, or especially in a pristine suburban garden, our immediate visceral instinct is to get rid of it. We fire up the chainsaw, we cut it down to use for firewood, or we remove it simply because it looks untidy, or we are afraid a branch might fall on a fence.
And that aesthetic preference has devastating ecological consequences. Every single time a landowner removes a standing dead tree, what ecologists refer to as a snag, they are directly, physically removing a potential breeding site for the Knysna woodpecker.
Wow.
They're removing the biological capacity for the species to reproduce in that area. When we think of habitat loss, we usually picture bulldozers flattening a pristine rainforest.
Yeah.
But sometimes habitat loss is invisible.
Yeah.
Sometimes it is just 1,000 suburban gardeners systematically, cleanly removing all the dead trees from an otherwise perfectly healthy landscape.
Death by 1,000 chainsaws. The forest is still there, but the nurseries are gone. So if the primary bottleneck for this adaptable bird is simply a lack of dead real estate, what is the action plan outlined by the conservationists? How do we fix this?
On a macro scale, the priority remains the preservation and expansion of formerly protected areas, safeguarding the remaining Afromontane forest, and preventing further clearing of the coastal white milkwood thickets.
Okay, the big picture stuff.
But on a micro scale, the localized actionable solutions are beautifully simple. The primary directive for landowners, forestry managers, and suburban gardeners within their range is preserve standing deadwood. Leave the snags alone.
I love that. The most highly recommended conservation action is literally to do nothing. Just put the chainsaw down and leave the dead, ugly tree exactly where it is.
Inaction is often the best ecological policy. And in areas where natural deadwood is genuinely scarce, perhaps in heavily managed plantations or highly manicured estates, the sources suggest that direct human intervention can be highly successful.
Like what?
Conservationists can install artificial nesting boxes designed to mimic deep cavities. Even more effectively, they can erect dead agave stumps, often called sisal logs, which have a soft, easily excavatable, pithy core.
Wait, they will actually use a wooden box built by a human or a random agave stump strapped to a post?
They absolutely will. The field data shows breeding pairs readily accepting these artificial substitutes, which yet again underscores their incredible behavioral adaptability. They just need the physical space to breed. They aren't precious about where it comes from.
That is fantastic. Okay, I want to pull the camera all the way back and synthesize everything we've unpacked today, because this has been a phenomenal journey analyzing the Camphothera notata. We started by looking at a creature subjected to unimaginable physical violence, surviving thousands of high-speed impacts a day thanks to a trabecular spongy skull, a tight fluid-free brain case, and built-in safety goggles.
And we observed how a singular evolutionary trade-off, a partially stiffened, flexible tail, allowed them to abandon the traditional vertical tree trunk.
Right.
This granted them the horizontal agility to scramble through dense canopies, acoustically hunting for termites, and deploying an incredibly long, sticky harpoon tongue that physically wraps around the outside of their skull.
We analyzed their architectural genius, dissecting how they specifically carve their tiny, downward-facing fortresses into the undersides of dead branches. A strategy that brilliantly utilizes gravity to drain rainfall and completely neutralizes climbing predators, even as they fight a brutal, losing evolutionary arms race against the parasitic, murderous chicks of the scaly-throated honey guide.
And we navigated the complex, often frustrating minefield of scientific data and field identification. We learned to locate them via the piercing skeed call and mechanical drumming. We decoded the diabolical juvenile trap where young golden-tailed woodpeckers masquerade as adult Knysnas. And most importantly, we learned a massive lesson regarding data literacy.
The 4-day fledgling myth, it really is a powerful reminder. The story of the Knysna woodpecker is fundamentally a masterclass in the necessity of looking closer. From learning to distinguish between a ventral streak and a ventral spot, to having the confidence to look at a highly respected global taxonomic database and say, no, a naked altricial chick cannot physically learn to fly in 96 hours. Critical, independent thinking is our absolute best tool for decoding the natural world. You cannot take a single data point at face value.
The natural world is far too complex for assumptions.
It really is. And that brings me to a final, slightly philosophical thought I want to leave you with today. Something to mull over on your own after we wrap up.
Right.
We spent a lot of time discussing how the future survival of the Knysna woodpecker, especially as it expands into heavily altered suburban areas, hinges almost entirely on humans simply choosing to leave dead, rotting, untidy trees standing in their pristine gardens.
It does.
It makes you wonder about the broader philosophy of how we interact with nature. We spend so much energy trying to actively save the environment with massive, expensive interventions, cleanups, and manicured nature reserves. But how much of true, effective modern conservation isn't about active intervention at all?
That's a good question.
How much of it is simply about us as a society learning to suppress our desire for absolute control and cleanliness? Perhaps the key to preserving the wild isn't building a better sanctuary. Perhaps it's just learning to tolerate a little bit of untidy decay, a little bit of natural, chaotic messiness right in our own backyards.
That is a profound shift in perspective. A healthy ecosystem is rarely a tidy one.
Exactly. Sometimes you don't need a grand plan. Sometimes you just have to let the dead wood stand, sit back, and let the little tiger woodpecker keep slamming its face into the tree thousands of times a day and surviving every single